So our goal today is to kind of continue what we started talking about last time, which is this kind of idea of, so you have a Markov chain and you want to understand the long-term behavior. So we want to understand the long-term behavior of, well, certain types of Markov chains. Okay. When I say the long-term behavior, I mean what percentage of time it spends in each state. Okay. Now, certain Markov chains kind of behave differently in this respect. So when I talk about certain types of Markov chains, we're not going to be able to handle every possible Markov chain, but we will be able to talk about some specific types of Markov chains that show up in a lot of problems. So, and also a lot of real-world scenarios. So specifically, we're going to look at regular Markov chains. So last time, I put the definition on the board, but I'll just repeat it here. So a Markov chain with transition matrix P is said to be regular if, well, so if there exists some power of this matrix such that every entry is positive. So if there exists a positive integer n such that p to the every entry of p to the n is positive. Okay. So specifically, we're going to be looking at matrices, or sorry, Markov chains, which are regular, and we're going to say, like, what is the long-term behavior of them? Okay. And this other thing came up last time called a stationary matrix. So this is kind of a key idea that comes up here. So the stationary matrix of a Markov chain with transition matrix P, so the same setup as here, is a matrix S, so it's a row matrix where the entries are S1, S2, up to Sk. So K is just the number of states, so let's just assume that our Markov chain has K states. So the stationary matrix is a row matrix like this with two properties. The entries of the matrix add up to 1. Okay. So you should think of the entries of this matrix as being like probabilities. So it makes sense that they add up to 1, right? And this word stationary kind of means that if you start with this matrix as your distribution and you apply the transition matrix, you get back the same matrix again. Okay, so this is the kind of stationary thing. Like if I started with that matrix, that distribution, so the stationary matrix, like if I started with these probabilities for each state, and then I apply one step of the Markov chain, so I multiply by the transition matrix, it gives me the same thing back. Okay. I guess one way to think of this, well, actually maybe I'll say, so the key fact here is for a regular matrix, or sorry, a regular Markov chain, the stationary distribution tells us the long-term behavior. Okay, so in other words, the chain well, the proportion of time, so if you run the Markov chain for a really long time, then the proportion of time in state J is equal to Sj for each state. So J is between 1 and K. We'll do an example in a second. I mean, I know this is all a little bit abstract at this point, but any questions about this? Okay, let's start with just a quick example here. Well, actually, one thing I should say here, at no point in this discussion have we talked about the initial state matrix, right? And that's kind of the cool thing here. When you have a regular regular Markov chain, then the stationary matrix gives you the long-term behavior, like regardless of the initial state. So actually, it doesn't matter what the initial state is. Eventually, as you run the process longer and longer, it'll start looking like the stationary matrix. The probabilities of being in any given state will look like the stationary matrix. And this is kind of relevant, though, because after we're done talking about regular Markov chains, we'll talk about something called absorbing Markov chains, which will be a different story because for absorbing Markov chains, it's going to be very important what your initial state matrix is to determine the long-term behavior. But for regular Markov chains, the initial state doesn't matter. Okay, let's do a quick example here. So if our transition matrix is, let's say 1/2, 1/2, 1/6, 5/6. Okay. So if this is the transition matrix of a Markov chain, then that Markov chain is definitely regular because so a Markov chain with transition matrix P for this P with this transition matrix. It's definitely regular, right? Because p to the 1, like just the matrix P by itself, which is just, so p to the 1 is P, has all positive entries. Okay. Now, in a few minutes, we're going to look at ways of actually determining the stationary matrix. So at this point, you haven't been taught how to do that. But I can tell you that the stationary matrix for this one is the matrix 1/4, 3/4. Okay. So actually, if we're doing like, like we said last time, you could probably guess from this picture which state is more likely in the long run, like which, just by sort of looking at, this column has more weight than that one, or sorry, less weight than that one in total. We did an example like this last time, and most of you guessed which state, is visited more in the long run. But finding these exact numbers is a bit trickier, right? Knowing exactly the percentage for each of them. So what this tells us then is, so in the long run, so if you start with any initial state, anything you want, and you just run this Markov chain for a really, really long time, and you count up how often was it in the first state and how often was it in the second state, basically, if you know the stationary matrix, then the proportion of time, well, yeah, the Markov chain is in the first state kind of 25% of the time if you run it for a really, really long time. So I'll just say in the long run. Okay, so apologies, that's getting close to the bottom of the board. But by the way, if I asked you to check that this is the stationary matrix, if I gave it to you and asked you to check it, what would you do? Yeah. Yeah, you definitely want it to add up to 1. That's the first criteria. Yeah, certainly if I told you this was a stationary, or I asked you if this is a stationary matrix, you add up the entries, it's not 1, you've got a problem and you should answer no immediately. What else should you check? Yeah. Yeah, exactly. So just to repeat that louder, all you would do here to check if this is the stationary matrix, so make sure it adds up to 1, and then check, just quickly compute. So you'd want to check that if I multiply it by p on the right side, that you get back the same matrix. Okay, so I'll leave that up to you to check, but yeah, we've done a lot of matrix multiplication, so that should be easy to check. Okay, any questions about any of this? Okay, so that doesn't tell you how to find the matrix, but we'll do that in a minute. Okay, let's do a trickier example. Okay, so consider the Markov chain. Consider a Markov chain with transition matrix P, which is, so now we're going to go with a 3x3 matrix. So 0, 3/4, 1/4, first row. Second row is 2/5, 2/5, 1/5, 1/5. And then we got 1/3, 0, 2/3. Okay. And so what we're going to do is, kind of first we're going to ask, is it regular? And secondly, we're going to find the stationary matrix. Okay. So we haven't done any of these yet, but if you wanted to check if this thing's regular, does anyone have a feeling where to start, what to do? Well, first of all, the very first thing is, if you didn't see any, if there weren't any zeros here, you could just be like, yes, it is regular, right? Unfortunately, we've got a couple of zeros, so yeah, what would you do? Maybe it's not a very fair question because I haven't showed you how to do this kind of thing. But what we want to determine is there some power of this matrix that has all the entries positive, right? So, I don't have a better idea other than let's just start taking powers of this matrix. So p to the 1 is no good, it has zeros, but maybe p squared will work, okay? And really, I don't have a better method than that. So, well, actually, maybe I do have a slightly better method. So actually, if you think about it, we don't actually, if we want to check if this is regular, we don't care what the entries of p squared are, like the actual exact numbers. We just care if they're positive or not, right? So here's a quick way to check. Well, it's not that quick, but so for part A here, so rather than actually computing p squared, it's kind of useful to just find out where the positive entries are. So p has the pattern in terms of where the zeros and the positives are. So it starts with a 0, then you have positive, 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 0, positive. Okay. And actually, just using this, we can find out the sort of pattern of p squared in terms of where the positives are and where the zeros are. So is it clear what I'm doing here? I'm just taking this matrix. Everywhere I have a 0, I still write a 0 to make this pattern. Everywhere I have non-zero, I just write a plus, right? Because there's no negative entries in these matrices. Okay, so p squared is going to look like, well, it's a matrix with this pattern times itself. So this is just the pattern for p and p again, right? So p squared is just p times p. Okay. And now you can basically like do matrix multiplication, but in a way where all you care about is whether it's positive or 0. You don't actually care about the values, right? Because we would like to see, if we see positive everywhere in this matrix, then we know that p is regular, okay? Any questions about that? I know that's maybe a bit vague. But, okay, so if I want to find out if this is positive, I take this row, right, and kind of multiply it down this column. So it's like 0 times 0 positive times a positive, and then plus a positive times a positive. And if you're just adding positive stuff, it's, it's always going to keep it positive, right? Oh, sorry. This is the one I'm doing that one. Okay, for this entry, I've got the first row times the second column. I see 0 times positive. That's no good. I see positive times positive. Once you see a single, like positive times positive, you know it's going to be positive, right? Because you're just going to keep adding more positives to it, right? Is it clear what I'm doing here? I'm just trying to get the general pattern. Okay, so 0 times positive, 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 positive. Okay, and if you kind of keep going, you will see that the whole thing ends up being positive. Okay. So by the way, so here I'm just doing this as sort of a fast way of doing this. If you computed p squared, if you computed all the actual entries, that's not wrong. There's nothing wrong with that. It's just that you're doing a little bit more work than you need to, right? Because then you're going to do a whole bunch of arithmetic, dealing with fractions and stuff, and you don't actually need to do that. All you care about is like whether it's positive or 0. Okay. Any questions about that? Yeah. Huh. That would seem a bit cruel to make you do that, right? So actually, we're going to talk about this a bit more later. So right now, I'm just going to look at examples where they are regular. So we're just how to show that. But actually, I think next class, we're going to look at an example that's not regular. And we'll see that. So if it's not regular, in principle, you could think, oh, maybe I have to multiply this. Like if I do it 10 times, it'll still have zeros. And then I do it 11 times, it'll have zeros forever, right? So obviously, you don't want to do it forever. Basically, if you have some sort of repeating pattern that comes back, and then you can realize that it's not going to be regular. But we'll talk about that more next time. So for now, I guess the answer is no. There's no obvious place where you can stop. But yeah, we'll talk about that more later. So anyway, for question A now, yes, it is regular, because all entries of p squared are positive. But yeah, that is a very good question, by the way. Okay. So now we're going to try to find the stationary matrix. So one thing I like about this part of the course, actually, is it's going to bring back a lot of stuff we've already done. So as it turns out, finding the stationary matrix just boils down to solving a system of linear equations. So the stationary matrix, so for part B, it's going to be S1, S2, S3, right? And we want it to satisfy, as was said before, right? You want S1 plus S2 plus S3 to be 1. And then you want S times P to equal S. Okay? But let's write this out in a bit more detail. Okay. So S times P would just be like this. Okay, so this is your S, that's your P, and you want that to equal S. So sorry, this is getting a bit crunched at the edge of the board. So this is just S, P, and S here. And we can basically, let's now do the matrix multiplication here. So if we take this times this, we get, so S1 times 0 is 0, S2 times 2/5. S3 times 1/3. So I'm just doing the matrix multiplication on the left side. Your second entry will be 3/4 S1 plus 2/5 S2, 0 S3, and then 1/4 S1, 1/5 S2, 2/3 S3, and we want that to equal S1, S2, S3. Okay. So this is just doing this matrix multiplication here. Now we go back to what we learned about matrices, where basically for two matrices to be equal, they have to have the same size, which they do, and each entry has to equal the corresponding entry in the other matrix. So for these things to be equal, what it means is that you must have 2/5. So basically, this is a system of three equations. This equals that, and this equals that. Okay, and 3/4 S1 plus 2/5 S2 equals S2. And then 1/4 S1 plus 1/5 S2 plus 2/3 S3 equals S3. Okay, so basically this matrix equation, it's kind of like when we did, when we were talking about like inverses, we said if you have a system of linear equations, you can turn it into a matrix equation and then solve it using inverses. This is the opposite. We have a matrix equation we can turn into a system of linear equations. And then we still have, don't forget about this one, right? We still have this equation, S1 plus S2 plus S3 equals 1. Okay, so what we have here now is a system of 4 equations with 3 unknown variables, right? Our unknowns are S1, S2, and S3, and we want to find them. As it turns out, you don't actually need all 4 equations. This is something that's always going to happen. So to find the stationary distribution, basically what you want to do, so you find your equations, your 4 equations. Out of these ones, so this one you need to keep. And out of these 3, you get to delete any that you want to delete. So remove one of these. Okay. And it doesn't actually matter which one you remove. It's going to give you the same answer either way. It turns out like you could keep all of these equations and solve it, but you don't actually need them all, basically. So in my notes, I chose to remove this one. So let's remove that one. And then solve the system of linear equations. So and once we solve this system of linear equations, it's going to give us S1, S2, and S3. And that tells us the stationary vector, or the stationary matrix. Okay, so this is the general kind of procedure. Okay, so let me just, I'll just to be clear, what I'm doing now is I'm solving this system. Actually, let's clean this up a bit. So it's always nice to have your, we're going to put this into a matrix. You want to have your variables all on the same side and all of your equations. So let's do that. So this equation becomes negative S1 plus 2/5 S2 plus a third S3 equals 0. And then we've got negative 3/5, no, sorry, negative a quarter. So I'm just doing this. No, I messed that up again. I'm doing this one. So 3/4 S1 minus 3/5 S2 equals 0. And those are my three equations. And like I said, we remove the last one, but it doesn't actually matter which one you remove. Any questions about any of this so far? I know, is the procedure sort of clear? Like, you set this up, you get a system of equations, and then you delete one and then solve it. Okay, let's put this in a matrix. Okay. Right? And then we just do what we always do, right? We do Gauss-Jordan elimination. So, okay. I'm going to, well, actually, what do you want me to do at this point in terms of what would you suggest to do this matrix? Yeah? I like that, yep. Right, because I'm trying to eliminate that -1 there. I might as well, just to make it a little bit faster, I'm going to also get rid of this 3/4 at the same time. So I'll take row 3 minus 3/4 row 1. 1, 1, 1, 1 still, and then 0. So I know those will be zeros. Right. So I kind of trust that you guys could do these calculations here. You guys are experts at row reduction by now, or Gauss-Jordan elimination. So, okay, 5/7 row 2, right? Just to get the 1, I want to get a 1 right there. Actually, at this point, how many of you feel confident you could reduce this system at this point on your own? Or how many want to see me do it? Okay, I'll keep going for a bit, and then there aren't actually that many steps to go. Okay, so what I've done so far, I got my zeros, my 1 and 0 in the first column. I got my 1 where I wanted it to be right there. Right, I'm now going to use that to eliminate everything else in this column. So We'll take row 1 minus row 2, row 3 plus 27 over 20, row 2. Okay. I guess maybe one thing I won't really do is actually do the calculations here, just for time. But I kind of trust that you guys could get these numbers. So it's 1, 0, 1 over 21 on the first row, and then 2 over 7, apparently. Okay, something like that. Two more steps. So I'm going to take my last row, get rid of this ugly fraction. Okay. Again, these are all, 28 over 15 times that number gives you that number. These are all things that, yeah, it's a pain to do the calculation, but I'm sure you guys can do it. If I take row 1 now, minus 1 over 21, row 3, and row 2 minus 20 over 21, row 3, I'm going to be left with, well, I know what it's on the left side. It's exactly what I want. It's the identity matrix. Then over here, it turns out this ends up being 4 over 15, 1 over 3, and 2 over 5. Okay. So after all of this, we have to kind of remember what we were doing. So what this tells us at the end is that S1, you have to remember the columns of this matrix correspond to our 3 variables, S1, S2, and S3. What this says is S1 is 4 over 15, S2 is 1 over 3, S3 is 2 over 5. So our stationary distribution is the matrix 4 over 15, 1 over 3, 2 over 5. Okay. Is that clear, or any questions about that? If you were doing this on your own and after doing all of these steps, you weren't that confident about your final answer, does anyone know how you would check it? Yeah. Yeah, definitely. I would like to. That's a good place to start. If they add up to something that's not 1, you know something went wrong. But that's not quite good enough. You need something else. Yeah. Yeah, exactly. Yeah. So, take this matrix, multiply it by p on the right side, and see if you get the same matrix back, right? If those things both happen, if it adds up to 1 and s times p equals s, then you know for sure your answer is correct. There's no other possibility. Okay. So now the cool thing is, from this, we can say, basically, if you run this Markov chain like a zillion times, right? If you run it basically infinitely many times, we can now say exactly how long it spends in each possible state. So basically, for example, so in the long run, I guess the long run always means, theoretically, if you ran this Markov chain infinitely many times, the Markov chain spends 4/15 of the time in the first state we didn't give these states didn't correspond to anything, but if they did, then you would, you could write what they correspond to. 1/3 in the second state, and then 2/5 in the third state. Right? So basically, if you keep running this 40% of the time, on average, like as you run it for a really long time, you'll see about 40% of the time the Markov chain goes to the third state. So 2/5 is 0.4. Okay. Any questions about that? And yeah, again, when we're talking about regular Markov chains, this does not depend on the initial state. Okay, so where you started doesn't matter. Okay, let's come back to this question of how many powers of the matrix do you need to check? So definitely checking p and then checking p squared is, I mean, for a lot of the time that is going to be enough, but it's not always enough. So unfortunately, sometimes you do have to check pretty high powers. So here's an example where checking p squared is not always enough. So for example, let's say P is the matrix 0, 3/4, 1/4, 1, 0, 0, 1/3, 0, 2/3. Okay. So basically the pattern of P, like in terms of pluses and zeros, it's 0 plus plus, plus 0, 0, plus 0 plus. Okay. So, I mean, I guess it's not surprising that taking the square isn't always good enough, but let's see what we would get if we take the square. So p squared is so this is just the pattern of p again. And so let's write that twice. So it's p times p, right? Okay, so let's do this. So 0 times 0, plus times plus. Once I see that, I don't actually have to keep going because we're just going to keep adding more zeros or pluses. So if I see 0, 0, plus, plus, once I see a plus with a plus, I know that's a plus. So I'm doing first row times the first column of the first row of P times the first column of P. First row of P times the second column, I see a 0 and a plus. Those cancel. A plus and a 0. Or sorry, they don't cancel, but 0 times anything is 0. I see a 0 again. So unfortunately, we've got a 0 here. Got a 0 with a plus, still 0, 0, plus. That's a plus. Right? Keep going, so plus, and a 0 makes a 0, 0, 0. I'm going to get a plus, and a plus. And maybe you can take my word for it that those are all pluses. Okay, if we were doing this, we would, like, we couldn't conclude anything at this point, right? We don't know if this is regular or not. So we kind of have to try p cubed. Now, if you want to find p cubed, you can just, well, p cubed is the same as p squared times p, right? So I can write down the pattern for p squared. And then write down the pattern for p. Okay. So this is p squared. I know that this is what p squared looks like because I already did it. It's up here. And this is p. In this case, you will see that, well, actually, no. It still doesn't work. So I'll let you maybe do this on your own if you want to check. But it's got a 0 right in the middle. Everything else will be a plus. But if you check p to the 4, it is all positive. So sometimes you have to take a lot of powers. But on Friday, we'll see an example where it's not regular, and I'll show you how to tell how many powers you need to take.